In this video, I want to take a look at another technique we can use to solve differential equations. In this case, we're going to be looking at linear first-order differential equations and using a technique called integration factor or integrating factor. So just a quick reminder, if we're talking about first-order linear equations, they take the form of the following. So linear first-order ODEs take the form of the following. So we're going to have a derivative, but that derivative can have some factor that is a function of x as long as it's not a function of y. So I'm going to have a1x times dy dx plus what I'm going to call a0 of x times y by itself, and that can be equal to some function on the other side, g of x. So the point is, it's first order because the highest derivative is a first derivative, and it's linear because there is no nonlinear term involving y. We have these functions that might be nonlinear terms of x, but there's no nonlinearity as far as the dependent variable y is concerned. So keep that in mind. This is the generic form of our linear first-order differential equation. If we divide the whole equation by a1 of x, we can force this leading coefficient in front of the dy dx term to be 1. And so this is something that you can essentially always do. The only thing you need to watch out for is possibly maybe there's some value of x for which this coefficient is a 0. But if this coefficient is a 0, that makes this whole thing be not a differential equation anyways, because this term is gone. So you need to worry about it being 0 because we're dividing by it, but at the same time you don't need to worry about it being 0 because if it was 0, we wouldn't have a differential equation, and in that one particular case, we could solve it as a simple algebraic equation. So dividing by this a1 of x term is going to yield the following. The nice thing is that we don't have, again, our leading coefficient becomes 1. We don't have this term up in front of everything. And this term, I'm going to call it some new thing. I'm going to call it p of x times y. And let's call this thing, instead of g, let's call it f of x. So what I've done is basically combine this a0 of x divided by the a1 of x. That's this term. So the thing I'm calling p of x, it's a0 of x divided by a1 of x. It was some ratio of two functions. Now I'm just calling it its own new name, its own new function. And similarly, the thing I'm now calling f of x is what I get if I take the old g of x and divide it by a1 of x. So it's just, again, some new function of x. So in general, you can always write a linear first-order differential equation in this form where the leading coefficient is 1. And that's going to make life a little bit easier. So this is sort of as generic as you can get. This is a linear first-order differential equation. This is the starting point I want to work with. Try as we might, we're not going to be able to separate the x and y variables in this particular case, the way that it's set up. So I have this x term over here. I would multiply by dx, which would be great. That would turn this into a dy, but suddenly this term would now have a dx in it. And I would try to get rid of that dx by dividing by dx, and that would get rid of the x dependence on this y here, but it would reintroduce it over here. So basically, because I have this p of x here that I'm wanting to get rid of to make this y stand out by itself without any function of x, if I divide by this p of x, it'll make this term more complicated. If I multiply this term by the dx to make it simpler, it'll make this term more complicated. So in both cases, undoing the dx or undoing the p of x will simplify that particular term, but it'll complicate the other term, and we won't be able to solve for y all by itself on one side of this equation. So in general, we can't solve or separate, I guess I should say, we cannot separate the x and y variables. We can't separate the x and y variables in general here. So this isn't going to work. The approach that we had before, a separable equation, isn't going to work in this particular case. So we're going to need a different approach. So I want to take a look at this. And what we're going to do is kind of go through a process. I'm going to explain an approach that we're going to use. And every step that I do may not make sense as we're doing it, but hopefully in retrospect, it'll make sense why we did it. We don't have the full big picture. So just keep in mind, as we go through and develop some of these techniques, oftentimes you're not going to see the intuition of why we're doing it this way right off the bat. But know that the person that was originally solving these types of problems hundreds of years ago probably was the same, except for the fact that they worked on the problem for months and months and months and got to know all the ins and outs of it before they finally came up with an approach that works. So just know, if you don't see all of these right away, that's okay, as long as you can understand them in retrospect and kind of understand the intuition and why pieces went where they did and why steps were taken in retrospect. So hindsight's what's important here, not necessarily your beginning intuition. Okay, so I want to start by looking at just the left-hand side of this equation. So let's look at the left-hand side. So I'm going to, again, abbreviate left-hand side as just LHS. You'll see me often write right-hand side as RHS. But if we just look at the left-hand side, we've got dy dx plus p of x times y. This first term is the derivative of y. This term, hopefully obviously, is y all by itself. And this p of x term in between is this coefficient, has no y dependence. It does have potentially an x dependence. It could also just be a constant, but it's a coefficient with no y dependence. And that's what's important, because otherwise, if it had y dependence, we would have a nonlinear equation here. And now what I want to think about is how we can reconcile all these different pieces. And so let me try to give you a little bit of intuition for about what I'm about to do. If you think back to Calculus 1, we came up with a bunch of different rules for differentiation. We learned how to differentiate polynomials using power rule. Then we learned how to differentiate products using product rule and quotients using quotient rule, and sort of complicated compositions of functions using chain rule. So we had all of these different techniques in Calculus 1 for taking derivatives. Now our goal, as we're solving differential equations, is to undo derivatives, do them backwards. And in a sense, as we do this integration, we want to think of those same rules that we use to differentiate and try to think of what is the reverse of that rule that will allow us to do integration. So we want to basically undo some of those existing rules. And in this case, what I see is I have over here a term that involves y prime, and over here I have a term that involves y by itself. And if you look at product rule from Calculus 1, you wind up with two very similar terms. And so that's going to be sort of the inspiration for this technique, is we're going to try to do product rule in reverse. So let's think about product rule. From way back in Calc 1. Product rule in Calc 1 basically says this. If I take the derivative d dx of some product, and I'm going to pick those two functions to be some function mu of x times some other function y of x. These are my product of two functions here. What do we get when we do product rule? Well, I get the first times the derivative of the second plus the second times the derivative of the first. So I'll get the first times the derivative of the second. So I'll write that as dy dx. And hopefully it's clear the The x dependence of y is sort of built into that. Plus, again, the second times the derivative of the first. So I'll write it as d mu dx times y of x, if we want to make it totally explicit. And you're welcome to use primes instead of Leibniz notation if you want. It doesn't really make a difference here. But this is what we're looking at. So this is what product rule looks like. And I want to look at this, what we have here, and compare it to what we have here. And again, this is where the inspiration is coming from. Notice the first term over here involves dy dx. Same thing over here. The first term here involves dy dx. It has this other piece, but it has a dy dx. The second term has some function and then a y. Over here we have some function, because I haven't specified what mu is, times y. So this is the inspiration. I've got something that looks awfully similar to what we've got sitting right here. If I can make them look exactly the same, well, then I know how to integrate this entire side, right? The integral of this just means undoing the differentiation. Undoing the differentiation would lead me back to the original product, this mu of x times y of x. So that is my goal. If I can get this, if I can modify it in some way so that it looks exactly like this, then I will have something that I know how to integrate. It's basically just going to be product rule in reverse, right? So we want to make, let me number these to make it a little easier. I'm going to call this original equation that we're looking at 1, or I guess it's an expression, it's not an equation. And this one down here, I'm going to call it 2. We want to make 1 look like 2 so we can undo product rule to integrate. So that's the idea. This is something I know how to integrate. I can integrate this because it's equivalent to this, and integrating by the fundamental theorem of calculus will just undo the derivative, essentially. So that's the main goal. Can I get this to look like this? Well, what do I have to do to make this look like this? The first term here is dy dx with a coefficient of 1. The first term here is dy dx with a coefficient of mu. How do I make this coefficient mu? Well, I must need to multiply this whole thing by mu. I can't just modify this one term. Whatever I do, I need to do to the whole side so that we can preserve our rules of algebra. So I'm going to just take this top equation and I'm going to multiply the whole thing by a mu of x so that it makes it look exactly the same. And that's going to modify this term here as well. I'm not going to just have p of x anymore. I'm going to have mu of x times p of x. And then we're going to have a rule that we're going to have to come up with to relate that to this d mu dx. So I'm going to multiply the first one up there, 1, by mu of x. And let's see if I can get this all on the screen at once. When I do that, I'm going to get the following. So I'm going to get mu of x times dy dx. And again, I'm just multiplying mu of x times this whole first equation here, plus mu of x times p of x times y. So they're looking closer. I've modified 1, so it looks more like 2. Now the first term here matches exactly with the first term here. The second term isn't there yet. But this is something that we need to enforce. We can't just pick any function to multiply by. We need to think of what is the function that will allow us to preserve this correspondence between terms here. Right? Whatever I pick for mu, it doesn't matter as far as the first term is concerned, but I have to pick a specific mu that'll make this term, d mu dx, look the same as this term, mu of x times p of x. So if we can make, or if we can find a mu of x such that our coefficient here of the y term matches the coefficient here of the y term, then we're set. So that such that d mu dx, the coefficient of this term, matches this term. It's equal to mu times p of x. if we can find a mu that satisfies this, so that this coefficient matches this coefficient, which is exactly what I'm stating right here, then we're set. So this is what we need to solve. What is this? It's another differential equation. So we need to solve this new differential equation. And that differential equation is d mu dx equals mu times whatever p of x is. But what is this equation? What form does it take? It is separable. This one is easy. We can use our techniques that we did before. So all I need to do is get all the mu's on one side and all the x's on the other side, right? We're using mu instead of y. There's no y involved in this equation. This is a differential equation for mu. So if I get all the mu's on the left, all the x's on the right, then we're good to go. So I've got d mu over mu on the left. I divide both sides by mu, and then I multiply both sides by dx to get p of x dx. I've got all my x's on one side, I've got all my mu's on the other side, and I can integrate both sides. And when we integrate both sides, on this side, I will get the natural log of the absolute value of mu. And on the other side, I can't do anything with this right now because I don't know what p of x is, but I'll just leave it written this way. Integral of p of x dx. If p is some function that I do indeed know how to integrate, then we're going to be fine. This will be easy. What's the next thing I need to do? I need to get rid of the natural log because we were trying to solve for mu. Again, our goal is to, can we find mu such that this relationship holds? So our goal is to solve for mu. I'm going to exponentiate both sides, and when I do that, this is the same as we did before, so I'll get e to the natural log of the absolute value of mu is equal to e to the integral of p of x dx. And technically, if you want to think about it, one of these two, when we integrated both sides, one of them had to involve a plus c. But we're not going to care about that plus c. We can set this to 0. And I'll try to explain that in just a minute, why we're allowed to do that, but you'll see. Essentially, the idea is, coming back up here to the original equation, wherever it was, we're eventually going to be modifying this equation here by multiplying everything by that mu, whatever mu we happen to find. If it has a constant in that mu, this plus c here would turn into a e to the c term, which would just be some other multiplicative constant sitting in front of this. So you could think of it as being a k in front of this if you wanted. Well, that k term would show up here because we multiplied this term by mu. It'd show up here because we multiplied this term by mu, and it would also show up here because we multiplied this term by mu. So I'd have a k here, and a k here. It'd be in all the different parts, and we could just cancel it all the way through. So that's why we don't care about this plus c term. We want this k to be 1. If we set this c equal to 0, that means this k is going to be equal to 1. We can keep it there if we want, but we're just going to wind up canceling it later anyways, so we might as well make our lives easy and just set that constant to 0. And by the same arguments that we had before, we can get rid of the absolute values because we exponentiated both sides. We already know this has to be positive anyways, and we wind up getting mu is equal to e to the integral of p of x dx. That needs to be the function mu that we multiply the entire original equation by. So we've solved for the appropriate mu. This is the mu that satisfies this differential equation. If I take the derivative of this mu with respect to x, I'll get back mu times the original p of x that we were looking for. And if these two things are equivalent, then that means that this coefficient here matches this coefficient here, and that means that basically we can easily integrate this whole mess to make it look like this. We can undo the derivative by integrating and reversing the product rule. So that is our goal. We found the appropriate mu. This mu, this function that we just found, is called our integrating factor. So this function mu of x equals e to the integral of p of x dx, I've got right here, is our integrating factor. And the idea is, if I go back and now multiply the original differential equation sitting way up here by that particular mu of x every single term, the left-hand side will transform into something that looks like the result of product rule. And how can I integrate it? Well, I can just undo the product rule. I can get rid of this derivative and wind up with something that looks like this. So if we multiply the original equation that looks like dy dx plus p of x y equals f of x by this particular mu, which is a function of x, we get a left-hand side that can be thought of as the result of product rule and therefore easily integrated. Okay, so it looks a little bit scarier than it really is. Hopefully it'll make more sense once we actually start doing some of the problems, but let's just assume that we're at this stage. Let's assume that we've done this. And let me keep going in sort of a generic form where we haven't specified what our p of x is, we haven't specified our f of x. So let's go through the problem totally generically. And then let's actually do some actual examples where we plug in real functions for each of these. Okay, so let's kind of recap this. So to recap, we start off with a function that looks like this. dy dx plus p of x, and I should say differential equation that looks like this, not a function. It looks like dy dx plus p of xy equals f of x. If we multiply it by this particular function, mu of x, the whole thing, we will transform the left-hand side into something that can be basically the result of product rule. So what we're going to do is multiply by mu of x, which happens to take the form of e to the integral of p of x dx. So I'm going to multiply every single term by that. And when we do that, we will get basically this term. Sorry, dropped my paper here. We'll get something, let's just do it generically. I think it'll be a little bit easier. Mu of x dy dx plus mu of x p of x y equals mu of x f of x. But this term, by design, the whole point of picking this particular mu is that this term right here looks like d mu dx. That was the whole point of solving this differential equation. We said mu times p of x is the same as d mu dx, and that's what gave us this particular function mu that we should be plugging in. So as long as we plug in that function for mu, this looks like d mu dx. And now the left-hand side of this equation looks like the result of product rule. So what this looks like is d dx of mu of x times y of x. And that's equal to mu of x times f of x. And we can integrate both sides of this. Integrating on this side is nice. It'll just get rid of the derivative that shows up. So I'm going to integrate this side And kind of cheat on notation here a little bit. I'm not going to use a dummy variable, so this is technically incorrect. I should use a dummy variable in here when I'm integrating with respect to this, but don't worry about it as long as the big ideas make some sense. And on this side, we'll integrate mu of x times f of x. So on the left-hand side, integrating the derivative makes them go away, and it shouldn't have a comma there. That should be mu of x times y of x, not a comma. So I'll be left with mu of x times y of x on this side is equal to this integral of mu of x f of x dx. And when we finally solve for y, all we need to do is, and we'll have a plus c. Don't forget a plus c that comes into all of this at some point. We will have a big ugly term over here that's this whole thing divided by mu of x. So we'll have the integral of mu of x times f of x dx, whatever that happens to look like, that whole thing divided by mu of x plus c over mu of x. And again, here is our mu of x. If you want, you can actually even go back and plug that in to get the solution in terms of this e to the integral of p of x dx. But in practice, all that's important is that we've solved for y. We're not going to want to use this as a formula. So we get this, essentially you can think of it as a formula, but don't treat this as a formula. What we're going to do instead is actually go through the process every single time we do one of these problems, and it will make a lot more sense, I think. So let's do an example, because this all probably still seems very, very abstract, to say the least. So let's do an example. Let's see this thing in action, because it's really not that bad. Okay, so let's do a relatively simple one. Let's do dy dx minus 2y equals 4. So the functions are p of x is just the number, -2. Our f of x is just the number 4. They don't actually have x dependence. We'll do one where they do have x dependence in a minute, but for now, let's just try this one and see how it goes. The idea is I need to multiply by an integrating factor, and to recognize that, I need to just see that this is recognized that this is linear and it's first order. If it's linear and first order, then this technique will work. So multiply by our integrating factor. And oftentimes I'll simply write IF for integrating factor. So what is our integrating factor? Our integrating factor, mu of x, is going to be e to the integral of p of x. What is our p of x? It's -2 times dx. And so in doing that, what is the integral of -2 dx? Well, that's just going to be e to the -2x. So there is my integrating factor, e to the -2x. I'm going to multiply this entire equation by e to the -2x, and we'll see what happens. So I'm going to have e to the -2x times dy dx, and then I'm going to have -2e to the -2x times y, and that's going to be equal to 4e to the -2x. And what I want to recognize is, presuming that we haven't made any mistakes when we computed our integrating factor, that we didn't make any mistakes in this integration, this left-hand side looks like the result of product rule. So let's check it out. This should look like d dx of e to the -2x, our mu, times y, where it's presumed that y is a function of x. And that's equal to 4e to the -2x. So normally we don't need to do this. This isn't a required step, but let's just check and verify that indeed when I take this derivative and we do product rule, that I do indeed get back what I have sitting right here. So let's just verify that this line and this line are in fact equivalent. So this is just a verification step that you don't normally have to do, but it's a good sanity check. What is d dx of e to the -2x times y? Well, what will we get? Knowing that they're both functions of x, I'm going to get the first times the derivative of the second. So I'll get e to the negative 2x times dy dx plus the second times the derivative of the first. But what's the derivative of the first? Well, what's the derivative of e to the negative 2x? The derivative of any exponential is itself, and then by chain rule, I'll pick up an extra factor of negative 2. So I'll get negative 2e to the negative 2x times just the y. And if I go back and compare what we've got right here to what we had right here, e to the negative 2x times dy dx, e to the negative 2x times dy dx. And for the second term, I have minus 2 e to the negative 2x times y, plus a negative, so minus 2 e to the negative 2x times y. So indeed, this term here is the result of product rule of this term here. And now we have something we can integrate. So I'm simply going to integrate both sides, integrate both sides, so integrate the d dx of e to the negative 2x times y dx term. We have to integrate the other side as well. Integrate both sides, and on the left, I'm just going to get e to the negative 2x times y. The integral and derivative cancel. And on this side, we actually have to do the integration. So what's the integral of 4 times e to the negative 2x? I know it's going to be e to the negative 2x, because the integral of e to the negative 2x involves e to the negative 2x, and I just need to figure out the appropriate coefficient. So how do I make the coefficient become a 4 when I take the derivative of this? Because, again, that's how I like to think about it. Instead of integrating this, let's differentiate this and figure out what is the appropriate factor here that would give us a 4 once we differentiate. So I'll get a negative 2. If I already had a negative 2 sitting there, I would pick up a factor of positive 4 and get this term right here. And then we can't forget our plus c. And the last step is to now solve for y. To solve for y, all I need to do is get rid of this e to the negative 2x that shows up over here. And to do that, I need to multiply both sides by e to the positive 2x. I mean, you could think of it as dividing by e to the negative 2x if you want, but I prefer to think of it as multiplying by e to the positive 2x. We'll cancel this. So if I just straight all the way through multiply by e to the 2x, every single term, e to the 2x times this term, it'll cancel. E to the 2x on this term will cancel, and I'll just be left with a negative 2. And then the last term is going to be c e to the negative 2x. And this is what I meant earlier when I said oftentimes the c winds up being the most important part of the equation, the most important part of the solution in this case. If we'd left off the c, our answer would just be negative 2, and we would leave off any of this dependence on x. It's this term, the plus c term, that winds up being the most interesting part of the equation once we actually solve for what y is. So here's our general solution to the linear first-order differential equation written right here. And if we had some sort of initial condition, we could actually solve for what this value of c is. And we'll do that in a subsequent example. But this is the process. For now, I just want to practice this process. So let's do another example. And on this next one, we will do an initial condition. So let's look at this one. So for this one, I want to look at, I'm going to move to prime notation instead of always using Leibniz notation. I'm going to write y prime over x plus 2y equals 1 with an initial condition of y of 0 equals 3. So this right here, this is our initial condition. It tells us the value of the function when x is 0. The y value is 3. Okay. So looking at this, it does not look like the form that we need it to be in. Remember, when we did this problem, when we started it all the way back up here, way back at the beginning, we said it needs to take this form, but we can always divide by whatever the coefficient here is of the derivative term to make the leading coefficient 1. And that was our starting point. We always started with the leading coefficient being 1. So I need to do that here. This is always the starting point for these integrating factor problems. We need the leading coefficient to be 1, and it isn't right now. Right now it's 1 over x. So what do I need to do to make this coefficient be a 1 instead of a 1 over x? let's multiply the whole equation by x. So first step is multiply by x to make the leading coefficient be 1. And so when I do that, I'll get y prime plus, remember I've got to multiply every single term by x, so I'll have plus 2x times y equals x. And now we have something where our p of x and our f of x both actually have x involved. They're both actually functions of x instead of just constants as they were in the previous problem. So we've got this in the form that we need. Again, this plays the role of our f of x, and this term right here will play the role of our p of x. So now we need to find our integrating factor. So multiply by our integrating factor, which is going to be mu of x equals e to the integral, of p of x. And what is our p of x? 2x dx. And so in this case, we wind up with an integrating factor of e to the x squared. When I integrate 2x, I wind up with x squared. So here is the factor that I need to multiply this whole equation by to get it so that the left-hand side looks like the result of product rule. So what we're going to wind up with is e to the x squared times y prime plus 2x e to the x squared times y equals x times e to the x squared. Okay. Sure enough, this left-hand side, assuming we didn't screw up, looks like the result of a product rule. And so I should be able to rewrite this side, or this left-hand side as the derivative of mu of x times y. So e to the x squared times y. And let's just kind of verify in our head instead of writing it out this time. What would happen if I took the derivative using product rule? I'd get the first times the derivative of the second. Well, here's the first times the derivative of the second, plus the second times the derivative of the first. Well, here's the second, and the derivative of this, when you take the derivative of e to the stuff, you get back e to the stuff times the derivative of the stuff, which would give you an extra factor of 2x. So by chain rule, indeed, this is the derivative of e to the x squared. So these two, the left-hand side is equivalent to what I've got written here, and the right-hand side is our x e to the x squared term. And we'd integrate both sides with respect to x. And on the left, we get e to the x squared times y. And on the right, we have to integrate this mess. Luckily, this isn't too bad. We can do this with a u substitution. If we didn't have this extra factor of x here, we'd actually be kind of out of luck. The integral, the integral e to the x squared is not an integral that you can do. It's actually related to something called the error function, and it winds up being its own kind of well-defined term. But luckily, because we have this extra factor of x here, we can integrate this one with a u substitution. So we're going to have the integral of x e to the x squared dx. And for this, what I'm going to do is I'm going to let u be equal to x squared. That means that du is going to be 2x dx. I have an x dx, but not a 2x dx, so let's turn that into a 2x dx. And to account for that 2 that I put there, I'm going to put a factor of 1/2 in front of everything. And now I've got this right-hand side, so the left-hand side isn't going to change. We're not touching that for the time being. But the right-hand side, I have my 1/2. I can rewrite this as e to the u, and here is my du, 2x dx. So my du. And that will be equivalent to, again, e to the x squared y is equal to 1/2. What's the integral of e to the u? E to the u, plus some constant, and then we'll just go back and plug in for the u. So we've got e to the x squared times y equals 1/2 e to the u, but our u was x squared, so e to the x squared plus c. There we go. And the last thing is to solve for y. To solve for y, I need to get rid of this term here, so I'm going to multiply the whole thing by e to the negative x squared to get rid of this term. and we'll get y times 1/2 e to the, so multiplying by e to the negative x squared will kill off this term over here. Multiplying by e to the negative x squared will kill off this term here and just leave me with the 1/2. And the last piece will be plus c times e to the negative x squared. So this is the general solution to the differential equation. Get it all on the screen at once. Okay, so this is the general solution to this equation, but now we need to apply our initial condition to actually solve for this particular value of c. So let me zoom in and apply that initial condition. So we're going to apply the initial condition. Initial condition. That said y of 0 was equal to 3. So what it's telling me is when I plug in x equals 0, it should spit out y equals 3. So when we plug that in, y will be 3, and that will be equal to 1/2 plus c e to the negative 0 squared. So I plugged in 0 for x, 3 for y, and this is what we get. What is e to the negative 0 squared? So negative 0 squared is still 0. E to the 0 is going to be 1. So this whole thing is just equivalent to 1/2 plus c. But that's equal to 3. So let's get to solve for c by itself. Let's subtract 1/2 from both sides. And what we'll wind up with is c being equal to 3 minus 1/2, which is basically 2.5 or 5/2. So our particular solution at the end of all of this, our solution is that y is equal to 1/2 plus, what was the value of c? 5/2 times e to the negative x squared. And this is our full solution for this particular problem. Okay, let's try one last problem here. It'll be kind of interesting before we move on, and down the line we'll maybe even come back to the idea of integrating factors. This isn't the last time we're going to see it, but let's do one last example. So for our last example, I want to look at dy dx equals 1 over 2xy. Okay, so let's look at this equation, and I want you to recognize something hopefully right off the bat. Over here I have dy dx, so just y prime by itself. On the other side, I have not a y, but instead a 1 over y. I also have this 1 over 2x, which doesn't affect the linearity, but I have a 1 over y. This is not linear. Not linear in y. And so we can't even begin to start one of these problems. This integrating factor approach only worked for linear first-order equations. And what we have right now is a nonlinear first-order equation, right? Not linear y because of the 1 over y term. Okay. However, what if instead of considering this problem, what if we consider the reciprocal? And what if instead of thinking of y as a function of x, we think of x as a function of y? There's nothing mathematically that disallows us from doing that. It's just a convention that we normally think of x as the independent variable, the input, and y as the dependent variable, the output. But there's absolutely nothing that says we can't think of them in the reverse. So instead, let's look at the reciprocal and think of x as a function of y. So when I take the reciprocal, we take the reciprocal of everything. And that's the nice thing about Leibniz notation. dy dx, when I take the reciprocal, becomes dx dy. And the reciprocal of 1 over 2xy becomes simply 2xy. This is linear in x, right? You can think of it as a function 2y multiplying our x, but now it's the x terms that I'm looking for nonlinearities in, and there aren't any. This is linear in x. So I'm going to rewrite it so it looks more like the ones that we're accustomed to seeing. If I just write it, dx dy, luckily that leading coefficient's already 0. Let's move this term over, so let me write it as minus 2y times x equals 0. So here's this same equation, just rewritten. I moved this term over to the left-hand side, and I moved the order of the x and y so that it looks like the coefficient of the x term is the negative 2y. And now I have a linear first-order equation in x with a leading coefficient of 1. This is something that can be solved using integrating factor. Again, how would you ever have known to do this? It's really something where you have to look at a problem over and over and over. I'm not counting on you necessarily having this intuition. Once you've seen it done a few times, then yeah, maybe it's something that is added to your bag of tricks. But I don't want you to feel bad if you didn't see this particular trick. And again, I don't want you to think of these as tricks, even though that's often how they feel. That's certainly how they felt to me when I was taking differential equations. All I'm wanting to do is try to build our mathematical intuition. That is the goal of all of this. And so once you've seen a trick once or twice, maybe one of these days down the line, if there's something you can't solve, it's a trick that you'll remember in the back of your mind and just say, well, let's just look at it from another perspective. What if I think of x as a function of y instead? So don't worry about it if you didn't see this trick from the get-go. It's certainly not something I ever would have recognized when I was taking differential equations. Hell, I don't know if I'd even recognize it right now without kind of being hinted in this direction. So just don't feel bad about something like that. This is probably trickier than a problem that I would give you on an exam, for example. Okay, anyways, long story short, let's actually solve this thing. We should be able to solve this with an integrating factor. So multiply by our integrating factor, and our integrating factor in this case is going to be a function of y instead of a function of x. So it's going to be mu of y equals e to the integral of our p of y now, which is negative 2y dy. And so I will get e to the negative y squared. There's my integrating factor. And so if we multiply by that, what we should get is the result of product rule. So I should get basically d dx of e to the negative y squared times x equals, on the other side, it's still a 0 because I multiplied this term through to all of these other terms. And so let me not skip steps. Let me just, just so I don't confuse anybody, let me go back and make sure I'm not losing anybody here. So I'm going to rewrite this as e to the negative y squared times my dx dy term minus 2y e to the negative y squared times the x term. And on the right-hand side, we still just get 0 because when I multiply 0 by e to the negative y squared, it's still 0. So here's me having multiplied through, and now I'll claim that this is the derivative d dy. The derivative, remember, it's with respect to y, of e to the negative y squared times x. That's equal to 0. And then we integrate both sides with respect to y. And on the right-hand side, I'm just going to get a constant. And on the left-hand side, I get e to the negative y squared times x. And when we solve for x, I will get that x equals c e to the positive y squared. And you could think of this as being a function that is, this solution is explicit in x, and it's currently kind of implicit in y. We could try to solve for y. Basically divide by c, take the natural log, take the square root, and if we wanted to get it back, we could solve to make it explicit in y. there was some reason to do that. Say if the initial condition, again, was given y is a function of x, wouldn't really matter. You could still plug that in, 0 for x, whatever the value is for y, and see if you could figure out what c needs to be. But in general, you may want to solve this for y. I'm not going to worry about that here. I'm going to trust that you can do the algebra if you needed to solve for y. But this answer is totally fine for this particular problem. Okay, so this is another technique. It's going to be a common one that we'll use quite frequently on these first-order differential equations. And it's definitely something I want you to make sure you get some practice with, but I also want you to understand this big picture idea. Look at the examples, but also go back and make sure you understand the whole point of picking this particular form of this particular integrating factor that we're multiplying by is so that we can treat the left-hand side as the result of product rule and basically do reverse product rule for our integration technique.